Okay, thank you for the invitation and the introduction. So this talk is about effective field theories of matters. So I know that most people in the audience is not condensed matter physicist, so I will spend good amount of time covering the backgrounds. But the main topic is effective field theories for what is called strange matters. Okay, so in condensed matter physics, we study physical properties of materials made of lots of degrees freedom. For example, here, this is a unit cell structure of a high temperature superconductor, and circles with different color just represent different atoms. And these atoms form some crystalline structure, and some atoms lose a few outer shell electrons, and those electrons become free, propagating inside the matter. And in most cases, the microscopic physics is pretty simple. We are just supposed to solve the Schrödinger equations for those electrons, which are subject to the potential created by those ions, and those electrons are subject to electrostatic repulsion. And I said those microscopic physics is quite non-universal in the sense that depending on what kind of crystal structure, what kind of atoms you use in your synthesis, this potential become very non-universal. So if you can ever fully diagonalize your Hamiltonian and look at the eigenstates, the eigenstate and ground state wave function will be very complicated and contains a lot of microscopic details. But we are not quite interested in understanding all the microscopic details. Instead, we are mainly interested in collective behaviors that emerge at long distance scales. And often it is very hard to predict what kind of collective behaviors emerge from a given microscopic Hamiltonian. And so sometimes we say, instead of trying to predict what kind of long distance physics emerge from a given microscopic model, we just focus on possible ground state that can emerge from some microscopic Hamiltonian and try to characterize long distance properties in that phase. Okay, so one of the main goals in condensed matter physics is to say classify different phases of matter and understand the low energy, long distance universal physics using effective field theories. Okay, roughly the different phases of matter can be classified by the number of low energy degrees freedom. So if you have a trivial insulator with a linear system size L, then insulator has a non-zero gap between the ground state and the first excited states. So therefore, the entropy will be exponentially suppressed at low temperature. So if you probe your system at temperature energy scale below that gap, then essentially your theory is empty. And there are more interesting gap state, like topological state. Example includes quantum Hall state and topological insulators. And those states have a non-zero gap in the bulk. So the bulk entropy density is equally suppressed with this exponential factor as in trivial insulator. But sometimes you can have gapless edge mode. Okay, so, and in that case, there's a sub-extensive contribution that comes from those edges that scales with the Pauli. So here, this is that gapless contribution. And then sometimes if a spatial manifold has a non-trivial topology, then the topological state can support ground state degeneracy. Okay, so there can be some constant piece. So topological state is, in a sense, a critical state. It includes some gapless degrees freedom, either in the form of edge mode or in the form of ground state degeneracy. And those low energy degrees freedoms are captured by topological quantum field theories, or if you have a boundary, your boundary CFT. And then there are states which support gapless excitations in the bulk. And although in condensed matter physics, the microscopic Hamiltonian doesn't have the Lorentz invariance, there are many cases where Lorentz symmetry or even supersymmetry dynamically emerges in the low energy limit. And if that is the case, then you have the familiar entropy density that scales with a T to the D being the spatial dimension, and you are dealing with relativistic quantum field theories. And then the main topic of this talk is metals. So metals have a peculiar property in that the entropy density scales linearly in temperature. I mean, not all metals, but some of the metals scales linearly in temperature in any dimension. So that means that in dimension greater than 1, there are far more entropy at low energy than relativistic counterparts. Okay, so, and we will see that this can be understood as arising from the presence of infinitely many gapless degrees freedom. So that is the main topic of this talk. So let's start with a simple example. So imagine we have a finite density of fermions. Okay, so in condensed matter physics, usually that fermions are electrons. It doesn't have to be electron. It can be neutron or something else. And suppose my Hamiltonian is just quadratic. In the momentum space, I have some energy dispersion. Say here I have chosen simple k square over 2m, and then ck is the annihilation operator of the fermion at that momentum k. And then the ground state, due to the Pauli exclusion principle, the ground state is given by filling the single momentum state from the bottom up to some energy level called Fermi energy. So for this isotropic dispersion, the ground state is given by filling those states below this Fermi energy. Here, this blue region is the occupied state, and the white region is unoccupied state. And this circle here is a one-dimensional manifold. In this case, is called Fermi surface that divide the occupied state and unoccupied states. So this is the many-body ground state in this non-interacting Hamiltonian. And then the excited states you can obtain by, say, removing some of the electrons below the Fermi surface and putting them above the Fermi surface. Okay, that is the excited state with the same number of particles. But the low energy excitations are the one where you deform the shape of the Fermi surface slightly near the Fermi surface. You take out the electron just below the Fermi surface and put them just above the Fermi surface by deforming the shape of the Fermi surface. So in this sense, the many-body eigenstates are labeled by shape of the Fermi surface or the occupation number of those single particle states. So in this sense, in the absence of interaction, the shape of the Fermi surface is rigid. It is basically a good quantum number. But now, if we turn on interaction, say two-body interaction where fermion with momentum k and k prime exchange some momentum and go to other momentum state. So in the presence of such interaction, of course, the occupation number of fermion at a given momentum state is not conserved quantity anymore. Pictorially, that means the shape of the Fermi surface now can fluctuate through because of this interaction. So naively, one might think that the nature of the ground state in the presence of such interaction will be very different from the ground state of non-interacting Hamiltonian. But then, remarkably, a large class of metals actually behave in a very similar manner as non-interacting fermion. And based on this observation, Landau in 1950s postulated so-called Fermi liquid theory. And then later in 90s, Shankar and Polchinski provided a more microscopic justification of Landau's theory based on renormalization group language. So the idea is the following. Suppose I consider a fermion that is created just above the Fermi surface with energy E measured with respect to the Fermi energy. And then in the presence of interaction, of course, this state will decay into more complicated state. For example, this particle can scatter into another momentum state with energy E1, while kicking an electron just below the Fermi surface outside the Fermi surface like this. So this is you create a hole. You remove the electron below the Fermi surface, and then you create a particle above the Fermi surface. So we call this particle hole excitations. Okay, so here removing electron at negative energy is same as creating a hole with positive energy. So here this final state has energy E1, E2, and E3, which must add up to original energy E. And then and E1, E2, E3 are all positive. And in the small e limit, the phase space available for the final state goes to 0 as E squared, because you have basically 3 independent variables and 1 constraint. So as a result, the phase space for the final state goes to 0 as E squared, and that limits the lifetime of this, the decay rate of this particle goes to 0 as E squared in the low energy limit. Okay, so therefore, as you go to low energy, these single particle excitations have longer and longer lifetime, and that can be be probed by looking at the spectral function. So spectral function is a function of momentum and energy. So it measures the probability for a particle with momentum k to have energy omega. Basically, you create a particle with definite momentum k, and then ask what is the probability for that state to have energy omega, right? So in the presence of interaction, this will have some energy distribution, say, which is peaked at the energy of that excitation, but it has some uncertainty width, and then the width determines the decay rate. And then from the previous arguments, the width goes to 0 as energy squared. So as you look at the particle closer and closer to the Fermi surface, the energy becomes smaller and smaller, and at the same time, the peak becomes sharper and sharper as E squared. So therefore, asymptotically, in the low energy limit, this spectral function approaches a delta function, and we often call this delta function a quasi-particle peak. And it's a signature that even in the presence of interaction at very low energy, you have a well-defined single particle excitations in your system. So this quasi-particle is, of course, dressed. It's not a bare particle, bare electron. It is dressed with many particle excitations. So its mass will be different, and sometimes the mass of quasi-particle can be 1,000 times heavier than the mass of bare electron. Nonetheless, it carries the same charge because charge is not renormalized. And furthermore, if you write down the many-body Hamiltonian at low energy in the quasi-particle basis, you can diagonalize your Hamiltonian in the number operator of the quasi-particle. So this is the single particle energy for the quasi-particle, and this is the interaction between the quasi-particle. But the interesting thing is here, there's only density coupling, right? There's no non-fold scattering. So quasi-particles are subject to interaction with each other. The energy of quasi-particle is influenced by the presence of other quasi-particles, but they don't suffer from momentum changing scattering. Okay, so in that sense, eigenstate, the quasi-particle provide the eigenbasis for the many-body Hamiltonian. And then at low energy, eigenstates are labeled by occupation numbers of those quasi-particles. Okay. And there are some important physical consequences. So one is a heat capacity. Question is, as you increase the temperature, how much energy you have to provide to the system. And at low temperature, unlike in relativistic system, you can create the low energy excitation anywhere on the Fermi surface, on this extended manifold of Fermi surface with, say, thickness T, because energy increases only in the radial direction, right? So therefore, the entropy and the heat capacity increases as T linear, okay? Instead of T to the D in relativistic system. And here is a heat capacity measured for copper metal. Here you plot C over T versus T square. So this straight line is a T cube contribution to the specific heat that comes from the lattice vibration. But what we care about now is this finite interception here, which measures the fermionic contribution to the specific heat. And this picture here is shown is the shape of the Fermi surface for copper. The thing is made of copper. And then another thing that people measure is transport. So you apply voltage. So you run electric current through the sample, and you ask how much voltage drop in the sample, and that is electric resistivity. And in metals, because of this periodic structure made of ions, the continuous translational symmetry is broken. So therefore, momentum is not conserved. For example, as electron scatter, the total momentum can change up by this momentum associated with the periodic structure, right? A is the periodicity, then 1 over A is basically the momentum that can be provided by this periodic structure. And because of this momentum non-conserving scattering, you can have a resistivity in the system. But in Fermi liquid, such scattering is also suppressed by the phase space, and it goes to 0 as energy square. So that's why electrical resistivity scales as T square in Fermi liquid. Okay, so let me pause for a moment to see if there is any question. Okay, now this was the review of the Fermi liquid theory that is for the a large class of matter. But then people realized that there are different types of matters that cannot be described by Fermi liquid theory. And here's one example. This phase diagram is for a superconductor based on iron here. So it's and this vertical axis is temperature, and this horizontal axis is chemical doping. Here, X represents the concentration of phosphorus that replaces arsenic in this particular compound. And then here, for small doping, the ground state is so-called spin density wave state. You can think of this as some kind of magnet where the spin of the electron is arranged in a particular pattern, breaking the spin rotational symmetry. And then as you raise the temperature, of course, the magnet melt into a disordered state, and that is the conventional matter. And then as you increase the doping, the transition temperature decreases. And at some critical doping, it goes to 0. And this is called the quantum critical point, because at this doping, even at 0 temperature, the system undergoes a phase transition as you tune this doping, okay? And then this yellow dome here refers to the superconducting state, okay? So this superconducting state is like a Higgs phase where the U1 symmetry is spontaneously broken. And then above these two broken symmetry state, you have matter. And then different color scheme represent different exponent in how the resistivity scales with the temperature. Okay, so in this light blue region here, the resistivity goes as T square. So this is as predicted by Fermi liquid. But then as you approach the quantum critical point, the exponent becomes smaller and smaller. So in this red region, marked as non-Fermi liquid region, the resistivity scale as T linear, almost T linear. Then as you can see, this non-Fermi liquid behavior sits right above the quantum critical point. So it is very natural to posit that this is caused by what happens at this quantum critical point. Okay, so this kind of behavior is often called strange metallic behavior or non-Fermi liquid behaviors. So as you can imagine from the name, I think it's not very well understood. It's strange or it's not Fermi liquid, but we don't, in many cases, we don't yet know what it is. Well, we know what it is, but we don't know how to solve it. I guess that's a more accurate statement. So what happens at that quantum critical point is the following. So suppose I tune some parameters in the Hamiltonian at 0 temperature. Okay, so this is some tuning parameter, say strength of interaction in your Hamiltonian. So when interaction is weak, the ground state is a state that doesn't break any symmetry. And then in the strong coupling limit, for example, say the system prefers to break some symmetry spontaneously. And then if that phase transition is a continuous phase transition, so a second order phase transition, then you see as you approach this critical point from the right, you see the correlation length of this order parameter become longer and longer, right? And then at the critical point, you have the system is on the verge of breaking some symmetry by developing some non-zero vacuum expectation value, and then this operator that is about to acquire non-zero expectation value fluctuate very wildly at all length scales, and that means in the system you have now some collective mode that is gapless. Gapless because the correlation length or correlation time is infinite. And then this collective mode will interact with the electron. So as electron propagate in the sample, it suffers from scattering with this fluctuating collective mode, and another way of saying that is this gapless collective mode mediate long range interaction between electrons, and in the energy space, those long range interaction translates into some singular interaction that diverges in the IR, and if those IR divergence is strong enough, that can overcome the suppression by the phase space in a way that the decay rate become greater than energy self. If that is the case, then the single particle state decays faster than before it has one oscillation, and then we say that the quasi particle is no longer well defined, and then the many-body eigenstate can no longer be diagonalized in this single particle basis. So then what we have to deal with is genuinely interacting field theories that describes the electrons and those gapless collective mode. Of course, we are living in 3-space dimension, but in condensed matter physics, we often consider 2D or 1-dimensional system because there are materials that have quasi 2-dimensional structure or quasi 1-dimensional chain-like structure. So we have freedom to explore different dimensions. And in 3D, of course, the generic Fermi surface is a 2-dimensional manifold. So in that sense, it supports the most gapless degrees freedom at low energies. However, in 3D, the interaction effects are usually marginal. So even if it grows as we go to low energy, it tend to grow only logarithmically, just as we have in QCD. So therefore, quantum effects in the IR is not very pronounced unless you go to exponentially low energy scale. In 1D, the quantum fluctuations are very strong. It's so strong that even in the presence of any interaction, Fermi liquid qualitatively breaks down. However, there's an additional simplification because there's only one direction in momentum space. The energy dispersion of fermion cross the Fermi energy only at discrete point. Okay, that's called Fermi points. And the low energy excitations near those discrete Fermi points can be well described by relativistic quantum field theory, because you just have a linear dispersion at discrete points. Okay, so you don't really have extended Fermi surface, and those low energy physics is captured by CFT in many cases. And 2D is a more interesting case. It is below 3D, so that instead of logarithmic flow, there's a power law flow. So as you go to low energy, the effect of interaction grows as power law. And furthermore, space dimension is greater than 1 dimension, so the manifold of the Fermi surface is extended. So you have this combination of infinitely many gapless degrees freedom that are subject to strong quantum fluctuations at low energy. So you expect to get something very exotic in 2 dimensions. So that will be the main focus of this talk. So to be concrete, let us consider one example where now this strange metallic state emerge. So suppose my underlying lattice is a 2-dimensional square lattice. So as you can see, it has this 90-degree rotation symmetry. Okay, the lattice has this 4-fold rotation symmetry. And then let us imagine having a quantum phase transition from a phase where this 90-degree rotation symmetry is unbroken to the phase where the symmetry is broken down to only 2-fold rotational symmetry. Okay, for example, lattice can be spontaneously elongated either in the x direction or y direction, and there are these 2 choices, and then those spontaneous symmetry breaking can be described by vacuum expectation value of one real scalar field, and depending on the sign of that scalar field, you can say it's elongated in one of the 2 directions. Okay, and then we can ask what happens to the fermions at this quantum critical point.
Can I ask a question here, Sik?
Yeah.
So is the picture that when you break the symmetry, is it the dynamics of the ions that's doing that, or are you imagining that the lattice is staying the same and the electrons are for some reason choosing to extend in one direction rather than the other?
Right. So they are coupled to each other. So if electron wants to break this rotation symmetry, then ion responds to that, and then ion also get distorted accordingly. So sometimes it's hard to pin down what is the main driving force for such phase transition, but there are examples where even if you freeze the motion of ion, the electron wants to break the symmetry. Okay, that's what I'm considering, for example, here.
Okay, thank you.
Yeah, but in real material, of course, this kind of rotation symmetry breaking is accompanied with structural phase transition as well, where position of the iron also breaks the symmetry. Okay, and then at the quantum critical point, this order parameter is dynamically fluctuating at with long wavelengths and very long time scale. So you can imagine very slowly varying fluctuations of this symmetry breaking field that is coupled with fermionic degrees freedom. And then we want to understand the fate of the system in the IR in such cases. So here I have wrote I have written down field theory for such system. So it's a rather busy slide, but just to be concrete, let's go through this one action. So here, Cj is a Grassmannian field of electrons, say with flavor J, and then K is a frequency K naught and two-dimensional momentum, and I'm using polar coordinates. So mod K is the magnitude of spatial momentum, and theta is the angle in the two-dimensional momentum space. And then this is the kinetic energy of those electrons, say fermion, and then energy. So Kf is the Kf of theta is the Fermi momentum in direction theta. Okay, and then energy of fermion vanishes when K is Kf, and then when K deviates slightly away from the Fermi momentum to the leading order, energy changes linearly in the deviation. So I kept only leading order term here in the spirit of the derivative expansion in the effective theory. And then Vf of theta is the angle dependent Fermi velocity. It dictates how fast the energy increases as you move away from the Fermi surface. Okay, so that is the kinetic term of the fermion. And then here, the second term is the kinetic term of this collective mode, the real scalar Klein-Gordon field. And when this acquires non-zero expectation value, it breaks this discrete rotation symmetry. And the C is the speed of this collective mode, which is in general different from the speed of fermion. And then here is the standard quartic interaction between those collective mode. And here, this most important term is this line here. It describes the interaction between fermion and the collective mode. So say fermion with momentum K can scatter into momentum K plus Q by absorbing or emitting collective mode with momentum Q. Okay, so this Yukawa coupling is describes the interaction between fermion and the collective mode. And at low energy, the typical momentum that this collective mode carries is much smaller than the Fermi momentum, right? And in that case, the angle of the fermion doesn't change much, right? If the fermion was initially here, and if this momentum of the boson is not that big compared to Kf, then the angle doesn't change much, right? It changes only up to Q over Kf. So, and that's why I put only one angle here in the Yukawa coupling. But the point is that this Yukawa coupling still can depend on the position of the fermion, in angular position of the fermion around the Fermi surface. Okay, and then you can also have the fermion coupling that depends on the angle of the fermions around the Fermi surface. Here, what I want to emphasize is the fact that in order to fully specify your low energy effective theories, you have to specify those coupling functions, not just coupling constant, but you have to specify, say, shape of the Fermi surface, Kf, what is the size of the Fermi momentum at each direction, right? And what is the Fermi velocity at each direction? And what is the strength of Yukawa coupling, etc. So, and these are all low energy data, okay? And this is due to the fact that you have infinitely many gapless degrees freedom around the Fermi surface. So one way to view this is view theta as some kind of continuous flavor, okay? And then you have infinitely many gapless degrees freedom labeled by this continuous flavor. And then your couplings depends on this flavor index in a way, right? So therefore, the space of theories is an infinite dimensional space of coupling functions. And then one has to study the RG flow in this space of coupling functions. And here I have just drawn one schematic RG flow. So here, this vertical axis is the Yukawa coupling function. And if we turn that off, I'm left with basically non-interacting fermions. And then we know within this manifold there is a Fermi liquid manifold of Fermi liquid fixed points. Okay. Sorry, this is not quite non-interacting. You can still have a fermion-fermion interaction, but this is an interaction between fermion and critical boson is absent, right? So then you have a manifold of Fermi liquid, and this manifold is already an infinite dimensional manifold because Fermi liquid can come with a different shape of the Fermi surface and different Fermi velocity, and also different fold scattering amplitude called Landau parameter. And then this manifold of Fermi liquid has some relevant perturbations. It's not really stable phases of matter. One is the superconductivity. So this dashed line is a superconducting instability that was discovered by Badin, Cooper, Schriepper in 50s. But this flow is usually logarithmic flow in Fermi liquid. So that's why usually in normal matter, you have to go to very low temperature, exponentially low in the strength of the coupling before you see superconducting state. But if you turn on, if your matter is at quantum critical point, and if you turn on the coupling between the collecting mode and the fermion, then that coupling is actually strictly relevant at low energy. So it grows as a power law as you go to low energy limits. So this vertical flow is a much faster flow. So presumably, the system will quickly flow towards some strongly interacting theories. And here, this green line is, say, manifold of non-Fermi liquid fixed points. Okay, and then presumably, even this non-Fermi liquid fixed point is unstable against superconducting instability, so that after a while, this flow approaches this manifold and flow away out of this manifold towards some superconducting state. Okay, and that's what we can imagine happening, say, from this phase diagram, right? So if you start from up here at high energy and then go below in energy, right? You approach the non-Fermi liquid state, and then eventually superconductivity sets on. But the RG flow, say, within this red window, energy window, is dictated by this flow here, okay? And the eventual goal is to understand this RG flow in the space of coupling functions, okay? So then, yeah.
Can I ask a question? So,
Sure.
So do you generically expect then the temperature that superconductivity sets in to be higher in this case?
Then in Fermi liquid?
Yes.
Right. So that is the expectation that one sees from this phase diagram, for example. So say this is a Fermi liquid matter here, far away from the quantum critical point, right? And then here, as you go down, superconducting temperature is so low, so it's very hard to actually resolve experimentally. But near the quantum critical point is very high. So that's why one of the reasons why people are very excited about this strange matter, because that appears to be one way to raise the superconducting temperature. So, presumably this kind of long-range interaction that mediated by this collecting mode plays the role of the glue between electron Cooper pair, and that's why TC can be higher at quantum critical point. But I think it's fair to say it's not completely understood yet. But that is the scenario that people are pursuing.
I see. Thank you.
Yeah. I mean, the reason why it's not entirely clear is that in non-Fermi liquid state, you don't have well-defined quasi particles. So electrons are more incoherent, and then even though the glue is stronger, when there's no well-defined quasi particle, those incoherency tend to have a pair breaking effect. So there's a competition, and that's why I say it's not yet completely well understood. Okay, but this is the goal. This is eventually what we want to achieve, to have a global picture of the RG flow in the infinite dimensional space of coupling function. and characterize this manifold of non-Fermi liquid fixed point. And we want to understand what kind of data we need to specify to pinpoint the location in this manifold, and what is the strength of the superconducting stability around that fixed point, how fast this moves out, and that is the whole program. But as you can imagine, this is a very hard problem. You have to deal with the functional RG for strongly coupled field theories. So people have been trying to.
Before you leave that, Sensei, can I ask one more question about that picture? This picture, as I understand it, is an aspirational picture. Is that right, or is that?
Yeah, that's right.
So, and is there a way to see on this picture in your phase diagram? You had a spin density wave thing going on. Is there a way to see in this picture why that would also generically be associated with superconductivity?
No, that's not generic. That's specific to that material. But there are quantum critical point associated with a different symmetry broken phase. So spin density wave picture, you have to add another axis. Okay, so there's another, say, I already have 4 axes here, but suppose I'm adding 5th axis. Okay, that 5th axis is the perturbation that associated with the gap of the critical mode, right? So if you move out of this, if you move into that 5th axis, you turn on that relevant perturbation, right? Then you kill this critical mode, and you flow to Fermi liquid and superconducting state.
So is a way to say it that if I had some special feature like nesting or something in my Fermi liquid limit, I would have a different instability direction down on that bottom plane, and somehow you're hoping to then, when you flow away from that Fermi liquid line, to exploit that other instability rather than the superconducting line.
That's right. Yeah.
Thank you.
Yeah. Okay, so because this is a very difficult problem, people have been trying to first simplify the problem, and this goes by the name of the patch theory. So idea of the patch theory is the following. So at low energy, the typical momentum of the collective mode is small compared to the Fermi momentum. So therefore, electron won't change its direction much by observing this collective mode with small momentum. So therefore, if I had an electron initially at this momentum, it won't leave this region at low energy. So therefore, for some purposes, like for the purpose of understanding single particle properties of electron, we may be able to just focus on this local patches in the momentum space. That is the spirit of the patch theory. And what we can do then is to, say, focus on one patch or 2 patch where the Fermi momentum is tangential to each other, the Fermi surface is tangential to each other, and expand your momentum around that particular point. So which point you choose is which area depends on which area you want to probe in the Fermi surface, right? And then here, little k here is distance away from this center of the patch. And if I expand my energy of the fermion, then in the K1 direction here, vertical direction, energy increases linearly in K1. By the way, this S is either plus or minus 1 that refers to either this right patch or left patch. Just for the moment, focus on the right patch here where S is plus. And then as you move along this K2 direction, energy increases quadratically because the Fermi surface is locally parabolic here. That is the kinetic term within the patch theory, and then remaining term is more or less the same. You have the collective mode, and then Yukawa coupling, etc. And then the reason why this patch theory is simpler is because, say, within the patch, I can treat this, say, Fermi velocity to be almost constant. Okay, so I scaled out. So I set it to 1, and also the Yukawa coupling here within the patch will be almost constant here, if I just focus on this patch. Okay, so then we can do more standard thing that we are used to do in relativistic quantum field theory. One of which is to do scaling analysis. So we can ask how the interaction, say, grows as we go to low energy. Okay, for example, we scale my energy frequency by, say, factor of b, where b is some factor less than 1. And then to make this kinetic term invariant, I rescale the momentum perpendicular to the Fermi surface k1 with the same scaling dimension 1 by factor b. But then in the tangential direction, because energy increases as k2 square, I have to assign scaling dimension half for k2, right? So you have to rescale your momentum, you know, in an anisotropic way, and that's because you have picked a particular patch. And then under the scaling, the kinetic term of the electron is invariant. And then if you look at the kinetic term of the boson, there's something funny here. Here I have, this is the relativistic user kinetic term of the Klein-Gordon boson. But then as we see here, the K2 has scaling dimension half, whereas the frequency and K1 has scaling dimension 1. So therefore at low energy, this frequency square and Q1 square is less important, it's irrelevant compared to the Q2 square. So and actually at low energy, this kinetic term is not important at all. And physically what happens is that the dynamics of the boson is mainly dictated by the particle hole bubble, right? You can imagine as this boson propagate, this boson is boson decays into particle hole pair, right? Because boson can be absorbed by particle. And then boson propagate more as a particle pair. Of course, it can be combined into boson, but this kind of processes strongly address the dynamics of the boson. So therefore, bare kinetic term is not important. So that's the physics that is reflected here. And you can also easily see that under the scaling, the Yukawa coupling is relevant. It has scaling dimension 1/4, and the other interactions are actually irrelevant. So the main message in this simple scaling analysis is the fact that under the scaling transformation that keep the kinetic term of the electron invariant, some of the kinetic term of the boson is irrelevant, while the interaction is relevant. So from this, you can already see that in the low energy limit, the interaction effect will become very important. So at the end of the day, you have to solve some strongly coupled field theories for this system. And in general, we don't know how to solve those theories. So people have tried to introduce some small parameter to find some regime of control. So the one thing that have been tried is 1/n expansion. So I mentioned that there's a flavor J. So in real system, those flavor usually refers to electron spin. But imagine the electron come with many flavors from 1 to n. And then hope is to solve the theory in the large n limit and then approaches the physical system in 1/n expansion. And we learned that in relativistic field theories, such as ON vector model or gross niveau theory, in the large n limit, the quantum fluctuation become weak, and then we can compute, say, anomalous dimension and those physical properties in the 1/n expansion perturbatively. However, it turns out that in the presence of Fermi surface, the 1/n expansion is not that simple. And what was realized is that even though I give a vector large n flavor to the fermion, the theory in the low energy limit behaves like a matrix large n model, such as a large n Yang-Mills theory. And in these cases, you know, for matrix large n, you have the problem of proliferation of planar diagrams, even in the large n limit. And we still don't know how to treat those infinitely many diagrams. So at the moment, the fate of the large n Lamb-Fermi liquid is still unsolved. So the reason why the theory behaves like a matrix model is the following. It's basically due to the fact that the Fermi surface is extended. So in this kind of, say, higher loop quantum processes, say, there's an electron that interact with this critical boson many times here. And then one of the paths is where this electron, say, at this location, scatter so that it stays on the Fermi surface without costing much energy. And this kind of presence of many soft mode for the virtual processes enhance those IR similarity significantly, such that actually this kind of planar diagrams are as important as the leading order quantum correction in the larger limit. So pictorially speaking, if you have a one say flavor index, there's a angle around the Fermi surface plays a role of the second flavor, okay? And then this fermionic field behaves more like a matrix field, and that's why even in the large N you have to include all the planar graphs. Okay. So and then another approach is dimensional regularization. As I mentioned earlier, if you go to higher space dimension, the quantum fluctuations are weaker in the IR, so we may be able to find some perturbative fixed point. But unlike in relativistic field theories, there's no unique way of extending the dimension, because you can tune the space dimension and the dimension of the Fermi surface independently. For example, our target theory is here. Here is a two space dimension that supports a one dimensional Fermi surface here. But you can go in many different directions. And it turns out that one way that is convenient is to go in this direction, where you keep the dimension of the Fermi surface fixed, but changing the embedding dimension of space. So here at this blue point is the system where they support the ring of the gapless point, which is embedded in the three-dimensional momentum space. Okay, and then you can approach this strongly interacting theory starting from this weakly interacting theory, and then use this deviation from, say, upper critical dimension as a small parameter. Okay, so in this case, for the case of the eigenematic quantum critical point that I mentioned, the upper critical dimension happens to be 5½ spatial dimension. So at this 5½ dimension between 3 and 2, the coupling between critical mode and the fermion is just marginal. And then if you go slightly below this upper critical dimension, you can access the interacting low energy theory in a controlled manner using epsilon as a small parameter. And and it turns out in the small epsilon limit, indeed there exists a non-Fermi liquid fixed point in the low energy limit. Of course, there's no conformal symmetry, but there's a scale invariance, and then a lot of physical observables are dictated by the critical exponents that you can compute order by order in epsilon. But one peculiar picture that arises in this theory is the fact that the epsilon expansion is not organized by the loop expansion. And this is due to the fact that some of the kinetic term is actually irrelevant. So there, for example, the boson kinetic term is irrelevant under the scaling that keeps the fermion kinetic term marginal. Also, therefore, you have to include some quantum correction from the outset for the boson kinetic term. For example, technically, when you say compute this kind of vortex correction or self-energy correction to the fermion, you have to use the dressed boson propagator to avoid IR singularity. Okay, so for this double line of the boson propagator is already a dressed boson propagator. So that's why the epsilon expansion is not in powers of coupling square, but it's powers of actually e to the 4/3. So it's expansion in fractional powers of the coupling. And then you can compute, say, spectral function. So this is a spectral function computed at Fermi energy. So in Fermi liquid, we expect to have a delta function peak, but in this non-Fermi liquid, you have power law singularity instead of delta function. And this kind of exponent is something one can measure experimentally. And then you can also compute those kind of anomalous exponent for thermodynamic quantities. So I don't have time for more non-perturbative story, but recently it was found that in some non-Fermi liquids, one can actually compute the exact critical exponents even in strongly coupled field theory, and based on so-called interaction-driven scaling. So this is kind of strong coupling approach. So as I mentioned earlier, under the Gaussian scaling, if you rescale your field and momentum such that the kinetic term is invariant, then we say interaction is relevant, right? And then you can try to start with scaling in which the interaction is marginal, because interaction is more important than kinetic term anyway. So why don't we first start with scaling in which the interaction is marginal? Then you have to choose different scaling dimension for your field and time frequency, and then under that scaling, some of the other kinetic term, say the frequency linear term in the fermion, is also irrelevant. Okay, so then you basically, as in the zeroth order action is your interaction, then you can include the kinetic term as a perturbation. So this is kind of strong coupling approach. And then in some cases, those strong coupling expansion works, and one can extract the exact critical exponent in some cases. But let me just summarize. So I talked about theories of metals. So the standard metals are Fermi liquid theory, and they are qualitatively similar to non-interacting fermions. And because of the limited phase space for scattering, but then near quantum critical point, you can have qualitatively different strange metallic states because of the presence of gapless collecting mode that mediate singular interaction in the IR. And then I talked about one example of low energy effective theory, and the presence of infinitely many gapless degrees freedom near the Fermi surface, combined with a strong low energy quantum fluctuation, makes the theory rather challenging. So for example, if you have a vector large N theory, it behaves like a matrix large N theory. And if you study dimensional regularization, sometimes you have to deal with the expansion in fractional powers of coupling. And I didn't discuss in detail, but there are some non-perturbative methods that are being developed based on some strong coupling approach. Okay, so thank you for listening, and I will pause for any question.